Concave mirrors and reflectors used in, say, telescopes and satellite dishes aren't just any old curved shape, and the shape they trace out isn't circular. In fact, concave reflectors like this one curve in the shape of what we call a parabola.
Only a parabola can focus incoming light beams to a definite focal point. Circular reflectors kind of focus the light, but not really all that well. So, what is a parabola? Well, in this video, I'm going to show you what a parabola is and show you some of the mathematics involved. I'll then show you how to build what's called a linear parabolic reflector. It's a little bit of maths, a little bit of science, and a little bit of art and craft all rolled into one. Let's begin by drawing a parabola on a Cartesian plane. A Cartesian plane has an x-axis and a y-axis, and you can plot points onto it using the so-called xy coordinates. The point 2, 3 means 2 across on the x-axis and 3 up on the y-axis, so it appears here. The point -4, 2 appears here. The x value is always given first. A parabola is the curve produced on a Cartesian plane by the general equation y equals x squared. Let's draw a parabola taking the x values from -5 to +5. Since y equals x squared, when x equals -5, y equals -5 squared, which is 25. We can plot the point -5, 25 on the graph here. -4 squared is 16, so the point we plot is at -4, 16. -3 squared is 9, so our next point is at -3, 9. If we keep plotting all the points, we end up with a smooth symmetrical curve. This curve is called a parabola. Now, if I'm going too fast, you'll probably have to draw a parabola yourself to really understand. You can learn a lot from teachers, but you can often learn even more when you practice something for yourself. If we now take the equation y equals 1/5 x squared, the values for y change. Let's now calculate the values and see the resulting shape of the curve. 1/5 of -5 squared equals 1/5 of 25, which equals 5. So our first point is drawn at -5, 5, which on the graph is here. 1/5 of -4 squared is 3.2, so the next point goes at -4, 3.2. 1/5 of -3 squared is 1.8, so the next point goes at -3, 1.8. If we continue plotting all these points, we end up with a flatter curve than the one we saw before, but this curve is also a parabola. You can compare the two parabolas if we place them side by side. Now, all parabolic concave reflectors can focus parallel beams of light to a focus point. The top one here focuses the light beams to the point shown. The bottom one, being more curved, has a much shorter focal length.
All satellite dishes, regardless of their size, are designed according to these mathematical formulas. There really is an incredible amount of mathematics that goes into the design of, well, just about everything.
We can actually calculate the focal length of a parabolic concave mirror using the parabola equation. We've already seen that parabolas follow the equation y equals something x squared. Mathematicians and scientists use the expression y equals ax squared, where the a can be any number. For example, this is the graph for a parabola that follows the equation y equals 1/4 x squared. This is the graph for the parabola that follows the equation y equals 1/10 x squared. And this is the graph for the parabola that follows the equation y equals 1/20 x squared. It turns out that the focal length of every parabolic reflector equals 1/4 of the denominator, the numbers being circled, if the equation is expressed as y equals 1 over a number, x squared. If you draw the graphs onto graph paper and measure everything in centimetres, a y equals 1/4 x squared graph has a focal length of 1 centimetre, since 1/4 of 4 is 1. and a y equals 1/10 x squared graph has a focal length of 2.5 centimeters, since 1/4 of 10 equals 2.5. So what's the focal length of a y equals 1/20th x squared graph? If you said 5 centimeters, you're correct. Let's now shine some light beams onto our parabolas. Focal length of 1, focal length of 2.5, and focal length of 5.
Let's now use our knowledge of the mathematics of parabolas to make a simplified parabolic reflector called a linear parabolic reflector using some graph paper, cardboard, and aluminium foil.
We're going to use the equation y equals 1/40th x squared, which will give us a parabola of focal length 10 centimeters. The parabola will be used to focus sunlight to heat up some water. Firstly, calculate all the y values of the equation for when the x values are between -20 and +20. This will take a few minutes. Then plot the points onto an A3 sheet of graph paper. Connect the dots to produce a smooth curve, and you'll have a parabola. Carefully cut the parabola out, making sure you leave a wide section at the bottom. Trace it onto some card, and then cut out 2 parabola-shaped sections. Try to use as little card as possible. Next, cut out a large rectangular piece of card measuring 46 centimeters by 15 centimeters. This piece of card will eventually be covered with aluminium foil to become the reflecting surface. To attach the 3 pieces together, you'll need to cut out some struts. The struts are cut out from squares about 5 centimeters wide. The squares are cut into triangles, and then a small square is cut out from one of the corners. The exact size doesn't matter, but the angles have to be right angles. One side is folded in one way, while the other side is folded the other way. You'll need about 8 struts. Paste or sticky tape 4 struts onto each parabola, and then attach the rectangle. You might find it easier if you get someone's help. Cut out a 48 centimeter by 15 centimeter length of aluminium foil and use glue to stick it onto the card. Finally, place a 10 centimeter long rolled up piece of paper through the hole in a rubber stopper and glue the stopper onto the reflector at its vertex. Parallel beams of light shining onto the reflector should meet up at the reflector's focal point.
If the parabolic reflector is placed outside and pointed directly towards the sun's light rays hit the reflector and focus at a point 10 centimeters above its vertex.
You'll know that the parabola is facing the sun if the rolled up paper is not casting a shadow. Remember, never look at the sun. A can of water placed here at the focal point is receiving direct sunlight and a huge amount of reflected sunlight, while this can nearby, our control can, with the same amount of water in it, is only receiving direct sunlight. It's really obvious when you look at it from underneath. The air temperature in the shade on the day that we filmed was about 22 degrees Celsius. After 10 minutes, the water in the control can reached about 33 degrees Celsius, while the can of water placed at the parabola's focal point had reached a temperature of about 46 degrees Celsius. To get the best results, you may need to adjust the position of the reflector every 5 minutes or so, since the sun is moving across the sky. All the instructions for this practical exercise are on the Linear Parabolic Solar Reflectors prac sheet.